Hi, Rebecca.
Hi,
How you doing?
good. How are you?
Doing fine. I got a couple people in here. Are you one of the people that's mad at me?
No, why?
Okay, because I graded the notebooks rather harshly.
The notebooks?
Lab.
Oh, I'm not in your lab class.
Okay, so I got about maybe maybe a half of the class that's not mad at me. Hi, Brian. How you doing? Brian? Brian, you new to this? Okay, guys, we're just gonna wait for other people to come in. You don't have any questions, do you? Either of you have any questions over what we went over last week? Oh, thank you. No, no, leave it in there. Sorry, I'm having tea delivered. Any questions over what we went over last week?
I think I just need more practice. I printed out the sheets and I'm working on them right now.
Good enough. Good enough
Hello,
for.
can you hear me?
Yes, Brian.
Okay. Hi, how are you?
Hi. Is this the first time here? I haven't noticed your
No,
name.
I haven't been on here very often because there's a few reasons. One, I'm kind of shy. Um, Two, I already took this class before, so I thought I was like I took this class before, but then COVID happened and I had a
Yeah.
lot of trouble. So a lot of the content I already know, but then when I took the test, I realized that I needed to go over some stuff again. So I'm here
Well,
now.
well, welcome. Uh,
Thank you. Hi.
we got a couple minutes here. What did you find you were having the trouble on, Brian? Not that
Give
I'm
me a
trying.
second.
Not that
Uh,
I'm trying to ignore you, Rebecca, but go ahead, Brian.
Sorry, I'm trying to get like this screen working again.
Okay.
Okay, I think I got it. Um, it was um, it was the one question from I think it was the aluminum foil one on the test. It was like they gave us they gave us the density of aluminum, and then I couldn't figure out how to solve. I had trouble solving that one.
It was more a logic problem. You had to realize what density is, and it's mass over volume.
Right,
Okay.
right, right. Yep.
So if you have the mass of the stuff and divide by the density, you get the volume, right?
Oh yeah. I guess I overthought that.
Sometimes that happens. So once you have the volume, you have the length and the width. You just don't
Hmm.
have the height, which is the thickness. So once you get the volume, divide by the length and divide by the height, you have the thickness.
Okay, yeah. I guess I definitely just overthought that whole scenario there.
Yeah, that wasn't, it's not, that is not an easy density problem because you don't think in those terms. You
Right,
know,
right.
it's, so yeah, it wasn't an, and actually the last one, the last problem was not easy as well. That one was a bear. That's the one where I gave you pyridine and told you how much nitrogen and water you got
Hmm.
back from it.
Hmm. Yeah.
What you had to realize is you had to do the mass percent of the water. There are two ways to do that problem. You could either figure out how many moles of water you have and multiply it by 2 because you have 2 moles of hydrogen for every mole of water, or you could figure out the mass percent of hydrogen in the water, multiply that by the whole mass, and you're able to get the mass of the hydrogen.
Right, and I remember because I did a whole bunch of work for that, but I think I knew because I had skipped a vital step because I know I didn't get that one right. But there was just I did like all the work. I found I think I did mass percent and I found the moles of like the compounds instead of them individually.
So did I give you points?
I don't know. I don't know how to check that.
Oh, all you got to do. All right, let me go. You doing okay, Rebecca?
Yep.
Okay. All right, let me go into here. Okay. Okay, are you seeing the screen now?
Yes. Yep.
Okay. All right. All you got to do is go into submission. All
Okay.
right. Go down to quizzes. And when you're in student view, this will be a little bit different. Okay.
Mm-hmm.
Go down to the one that you want to see. In this case, it would have been test one. Test one. Click on that and wait. Crap. I can't, I'm doing this. View as a student. I'm viewing this.
I'm on the screen before right now. I'm on the quizzes section, so I can probably just play with it a little bit and
Okay.
find it.
Go up, click on submission review. Okay. Click on quizzes. Are you in quizzes, Brian?
Yeah. I found test one.
Okay, you found test one. Now, I think you click to the right of it. Yes, absolutely. You click to the right of it, and you don't click on the test, because if you click on the test, you just get the questions.
Yeah.
You click on the arrow besides the test, and you see in my screen, you get submissions and reports.
Yep.
So click on submissions, and then you'll get another box that pops up. Click on attempt. And basically, I don't make any comments when you get it right. I only make comments when you get it wrong. So those ones you'll have feedback on.
Oh, okay. I see it. Thank you very much. I see it all.
No problem.
Perfect.
So you've seen the light, huh, Brian?
Yes, I think I finally see it.
Okay, good. All right, Dylan, Joseph, Rebecca, any questions about what we did last week?
Nope.
No, but that one question was really weird. I think Dana did it. It was the really long one.
All right,
On the
one
PowerPoint?
question, it was
like what was it? It was like the alloy something goes into a liquid and then the precipitate of it comes out.
okay. That wasn't on the test. That was on actually one of the problems.
Yeah.
Is that what you're
That one was-
talking about?
Yeah.
Basically, you got to strip away all the crap, Rebecca. You got to strip away all the crap from that. And what you have to look at is what was produced and how many grams of what was produced. And
Oh, so just trying to make a chemical equation out of it? Just try to...
no, you don't make a chemical equation out of it. What you do is, like, say, for example, on the one thing, eventually you produced, I think it was tin 2 oxide or tin 4 oxide, one or the other. Do you remember that?
Yeah, I think it was that one.
All right. So what you do is you get a weight of tin oxide. Okay. That's how much you recover. All of the solder, all of the tin in the solder was turned into tin oxide. So you got to figure out what the mass percent of tin oxide is. Multiply that by the weight of the tin oxide. That gives you the weight of your tin.
Oh, okay.
All right.
Mm-hmm.
Anybody else have anything else? Anything else? Okay. Blake and Dylan, you're both in my lab, right?
Yep.
I am.
Okay. Do you remember my giving you the talk on the notebook first day of class?
I do.
Okay.
Yep.
Okay. I just wanted to make sure. What happened is, if you remember that first class, I couldn't record it. Or what happened was the recording got destroyed because I tried to record at the same time I was publishing my lecture, and that got destroyed. And that's where a whole lot of your classmates that didn't attend that lecture got lost on the notebook. So unfortunately, I got to give that lecture again. But it may help, may not. We'll see what happens. Let's see where I'm at. Okay, you guys are seeing the screen, right?
Yes.
Are you
Yep.
seeing the PowerPoint screen?
Yep.
We're good with that, guys?
Yep.
Everybody's seeing the PowerPoint slide.
We are.
Yeah,
All
I can
right.
see it.
So just as a review of what we did last Thursday, we decided that we were going to do stoichiometry. What you need for stoichiometry is you need a balanced chemical equation. So that's one of the things you need. You also need to know about moles, because in the stoichiometric, in the balanced chemical equation, you have the ratio of moles of one thing to moles of the other. So when we're doing stoichiometry, it's a three-step process. Turn your grams of your known. Your known will be given in the problem. Turn your grams of known into moles of known by dividing by the molecular weight. Second step, turn your moles of known into moles of unknown using the coefficients in the balanced chemical equation. That's called the molar ratio. Then once you have the moles of your unknown, turn it back into grams by multiplying by the molecular weight of the unknown. Any questions on that part so far? All right. Now, I believe I got through the first little bit of limiting reagent. Did I not?
Yes, you did.
Okay. So I'm not going to go through these particular slides, but what I am going to do is I'm going to give you another analogy. Okay. Dylan, you have 24 slices of ham. And this is going to be amazingly familiar to those of you that did the quiz. You have 24 slices of ham and you have 20 slices of bread. How many sandwiches can you make, Dylan? 24 slices of ham, 3 slices of ham per sandwich. We have 20 slices of bread. How many sandwiches can you make?
Eight.
Everybody agree with that? Why can't you make 10? You have 20 slices of bread.
Because there's 3 pieces of ham per sandwich.
Well, that still doesn't explain. Why can't you make 10 sandwiches? You have the bread.
You don't have enough ham.
You don't have enough ham. You're limited by the ham. So as a consequence, because you're limited by the ham, you can't make 10 sandwiches. You can only make 8. We are limited by the fact that we run out of ham. Same thing is true in chemical reactions. If you're given 2 amounts of 2 different reactants, then what you have to do is you have to figure out which one runs out first. Whichever one runs out first is the limiting reagent. That's the one you report out. Now, the corollary to that, Rebecca, you agree with Dylan that you can only make 8 sandwiches?
Yes.
Okay. The question I have to you is how much bread's left?
2 slices.
Ah, you did the same mistake somebody did earlier. How many slices are there per sandwich?
2.
And you have 2
4.
Okay. Now, the way you figured that out, you said, okay, I can make my 24 slices of ham, 3 slices, I can make 8 sandwiches, right?
Yep.
But I use up 2 slices of bread per sandwich, right?
Mhm.
Right, guys?
Yes.
So if I make 8 sandwiches, I've used up 16 slices of bread. How many did I start with?
20.
So I used up 16 of those 20. I have 4 left. That making sense, guys? So what we're going to do is not only we're doing limiting reagent tonight, but we're going to also determine how much of the excess reagent is left. And we're actually going to also do experiments. Not really, but we're going to pretend we're doing experiments. We're going to do experiments, find out how much we got from the experiment, And we're going to compare it to how much we should have gotten through the stoichiometry. And we're going to determine what the percent yield is. So that's what we did and what we're going to do. So, Brian, if I go to my pantry, my recipe is 4 cups of flour, 3 cups of apples, 1 cup of sugar, and 1/10 a cup of spices. That'll make 14 apple tarts. You with me, Brian?
Could you say that again?
Look at the screen.
Oh, okay. I see.
4
Yeah,
cups of flour, plus 3 cups of apples, plus a cup of sugar, plus 1/10 of a cup of spices are going to make 14 apple tarts.
yeah. Okay.
What happens if I go to my pantry and I only have 2 cups of flour? Can I make 14 apple tarts?
No.
How many can I make?
You would only, well, you have half as much as flour, so
So how many apple tarts?
7.
7. Okay. So if I use up my 2 cups of flour, how many cups of apples am I going to have to use up?
Half of that.
1.5 cups of
So
apples.
yeah,
Okay. If I started with 3 and I used 1.5, how many are left?
oh, 1.5.
1.5. Okay. Blake, my sugar. I start with 2 cups of flour. How much sugar's left?
So it'd be half a cup.
Half a cup. Easy enough, guys. That's all we're doing. That is all we're doing. We were limited by the flour. That means each one of the other things has extra amount to it. All right, chemistry is going to work the same way, guys. I'm going to have 2 different things. I'm going to be able to recognize a limiting reaction problem by the fact that I'm given amounts of 2 different reactants. If I'm given amounts of 2 different reactants, then one of them is going to limit the other one. And I'm going to use the limiting reagent to tell me how much I can produce of my products. Okay, I have 5.62 grams of calcium chloride and 5.23 grams of silver nitrate. How much silver chloride can you make? Okay, let's think about this. What am I mixing together, guys?
Calcium chloride and silver nitrate.
I'm mixing together calcium chloride and silver nitrate.
Professor,
Yes,
I think we already did this one.
we did this one.
Yeah, that's the last thing I wrote.
Sorry.
Good.
Okay, sorry, guys. All right. All right, second one. I have 190.1 grams of ammonium chromate and 184 grams of copper chloride, copper 2 chloride. What is the limiting reagent? Well, this problem gives it to you right away that it's a limiting reagent problem. But if it didn't have that second question, what are you mixing together? Joseph, what are you mixing together in this problem?
All right.
What are you
Mixing
mixing?
The aluminum chloride and the copper chloride.
The ammonium chromate and the copper chloride. Okay? So the first thing we got to do is we got to put down the reaction. So our ammonium chromate and our copper 2 chloride are our reactants. Joe, copper 2 chloride. What's the charge on the copper?
Charge in the copper is 2.
2. So how many chlorides do I need?
2.
I need 2 chlorides. Okay. Do you know what chromate's charge is?
No, I don't.
It's not one of the ones I asked you to memorize, so there's no reason for you to have known it. It is -2. Okay? Do you know what the charge of NH4 is?
1 second. +2. No,
No.
it's 1.
1 plus 1. So the charge on the CrO4 is -2. The charge on the NH4 is +1. What do you have to do to balance it?
Times the NH4 by 2.
Put parentheses around the NH4, subscript of 2.
Yes.
Okay? So copper's +2, chromate's -2, we're balanced. NH4 is +1, Cl's -1, we're balanced. So we get to the point where we have balanced the chemicals electronically. Okay, done with you, Joe. Dylan, how many NH4s do I have on the left?
On the left,
Left, where my arrow is.
just one.
Just one?
Two. I lied.
Okay, how many do I have on the right?
4.
No. NH4 is the whole cation. That 4 doesn't modify how many there of the cation there are. That modifies how many hydrogens are within the NH4. The whole NH4 is the cation. So how many NH4s do I have on the right?
4 or 1. Sorry.
Thank you, Dylan. You just saved me from pounding my head on the wall for 15 minutes. So, Dylan, if I have 2 NH4s over here and 1 over here, what number goes in front of the NH4Cl?
2.
Coppers are equal. My chromates are equal. And I now have 2 chlorines. And if I put a 2 in front of here, I have 2 chlorines. I am balanced. So that was the first thing. We did all that to make sure we got a balanced chemical equation. We need that to proceed. So I have my balanced chemical equation. Somebody yell out. What do we do next?
Do we change the grams to moles?
We're going to change each one of these grams to moles. Now, the strategy we're using for limiting reagent is we're going to pick a product. We're going to pick the same product for ammonium chromate and copper 2 chloride. And we're going to figure out how much ammonium chloride the ammonium chromate will make, and then how much ammonium chloride the copper 2 chloride will make. The one that makes the least came from the limiting reagent, and that's the one we report out. So if I do my moles of ammonium chromate, I get 190.1, divide that by the molecular weight, I get 1.251 moles of ammonium chromate. I do my copper 2 chloride, divide that by 134.45, I get 1.370 moles of copper chloride. So I got the moles. First step in stoichiometry, find the moles of your knowns. What's the next step?
Convert it to moles of the unknown
How do I do that?
using the molar ratio in your chemical formula.
Okay, what's my molar ratio? Let me see, my formula is, what's my molar ratio between ammonium chromate and ammonium chloride?
Is it 1 to 2?
1 to 2. I make 2 ammonium chlorides for every 1 ammonium chromates. How about copper chloride to ammonium chloride?
1 to 1.
What's the subscript in front of the subscript? What's the coefficient in front of the copper chloride?
1.
In front of the ammonium chloride?
Oh, 2, sorry.
So the molar ratio between the two is going to be?
1 to 2.
It's going to be 1 to 2 for both of them. Okay, so I am going to multiply my moles of ammonium chromate by 2/1. I end up with 2.502 moles of ammonium chloride. I do the same thing for my copper chloride. I end up with 2.74 moles. Now, I've got, if I use my ammonium chromate, I get 2.5 moles. If I use my copper 2 chloride, I get 2.74 moles. Do I have to multiply by the molecular weight of ammonium chloride at this point? Can you tell me?
No.
Can you tell me which one is the limiting reagent by the work I've done so far?
Yes. Yes.
Okay, guys, if you get to this step, if you have to understand that I'm going to be multiplying moles of ammonium chloride by the molecular weight of ammonium chloride in both instances. That number is going to be the same. So at this point, when you get to the moles of your unknown, do the comparison there. Which one's smaller, guys? 2.74 or 2.502?
2.502.
So that's the only one. That's got to be the limiting reagent, and that's the one I use to figure out how many grams I get. So at this point, and I didn't do the final math on it. At this point, I'm sorry, where am I at? Yeah. At this point, the question was, what's the limiting reagent? And we have that information just by the fact that we have the 2.502 moles of ammonium chromate. That is the limiting reagent. If I wanted to determine how much of the ammonium chloride I produce, I would just have to take ammonium chloride, and that is 35.5 plus 4, 39.5 plus 14, multiply it by 53.5. That would give me my grams of ammonium chromate. Questions? I have 1,816 grams of oxygen and 604 grams of octane. I have a balanced equation there. How many liters of carbon dioxide do you generate at STP? Now, do I have a relationship between liters and moles if my gas is at STP?
Yes.
So a good strategy here would be to find out how many moles of CO2 I have. But I have two amounts of each of my, I have an amount of each of my reactants. So I got to figure out how many moles my octane of CO2 my octane will make and how many moles of CO2 my oxygen will make. First thing, divide the oxygen and the octane by their molecular weights. Anybody want to take a guess? Anybody want to bet the next quiz? Which one's going to be the limiting reagent? Come on. Take a dare.
I'll do it. I'm a risk taker.
You're a risk. Who is this?
David.
Which one, David?
I'm going to go with the octane.
Ah, you cheated. You
How
looked
did I
forward, didn't you?
No, I can't see that well. No.
Okay. I got 56.75 moles of oxygen, 5.29 moles of octane. It would appear there's so much, there's 10 times more moles of oxygen than there is octane. So
Right.
it would appear that the octane is going to be the limiting reagent.
Right.
But we actually do the molar ratios. And lo and behold, that 56.75 turns into 36.32 moles of CO2. Whereas the 5.29 moles of octane turns into 42.3 moles of CO2. Which one is smaller?
The oxygen.
So which one is the limiting reagent?
The oxygen.
I love this example because 90% of the people, if they look at this, they think automatically, oh, octane's got to be the limiting. This is why you have to take it through that next step. You have to take it through the molar ratio step before you can figure out what your limiting reagent is. Now, as somebody said earlier, all I got to do is take my 36.32 moles of CO2, multiply it by 22.414, and my final answer is going to be 814 liters of CO2. And that's wrong significantly figure-wise. Actually, this is going to make a whole lot of difference. 814.1 liters of CO2. Any questions on limiting reagents, guys? They're not that hard. They're not that hard. They're a pain in the ass. Yes, they are a definite pain because you've now taken one problem and made two problems out of it because you got to take both of the reactants and figure out how much of the product is. But it's fairly easy once you get to that point. Once you figure out how much product you have, just compare the two. The smaller ones comes from the limiting reagent. Any questions about this? Are we good, guys?
Yep.
Okay. Do I need to go through another one?
That would be kind of helpful if you could.
This will be quick, Brian. And fairly easy. And you're going to do it.
Oh, no.
Okay. How many grams of HCl do you need to react completely with 227 grams of magnesium? Brian, can you relate a reactant to a reactant?
No. You can.
You can, because these coefficients, the coefficients that are in front of the reactants are just as balanced as a reactant to a product. You can even do product to product. All you have to do is have a balanced chemical reaction, and you can relate one reactant to a reactant, a product to a product. You can relate a reactant to how much product it makes, or you can take a product and say, okay, how much reactant does it take to make this much product? You can do any one of those four types of problems because you have a balanced chemical equation.
I never knew that until now. That's very helpful.
Okay, Brian, what's the first step of any stoichiometric problem?
Change grams to moles.
Okay, do you know what the weight of magnesium is?
No, I don't have it in front of me right now.
24.31. So I take that number of grams of magnesium I started with, divide it by 24.31. I end up with 9.34 moles of magnesium. Now, Brian, what's my next step?
You have to find the mole ratio, right?
Yep. What is my molar ratio, Brian?
2 or 1 to 2.
1 to 2. So what's going to go on top? If you're reading your chemical equation correctly, 1 mole of magnesium reacts with 2 moles of HCl to make 1 mole of magnesium chloride and 1 mole of hydrogen gas. So if I have moles of magnesium, and I know 1 mole of magnesium reacts with 2 moles of HCl,
But
does a
2
go ahead.
But 2 be on top?
2 moles of HCl is on top, 1 mole of magnesium is on the bottom.
Right. Okay.
So I get this down, I get 18.7 moles of HCl. I was asked how many grams of HCl. What do I do with this now?
do you find the molar mass of HCl?
H is 1, Cl is 35.5, so I multiply this number by 36.5, 36.45, and end up with 682 grams of HCl. You've done a stoichiometric problem, Brian.
Thank you.
Great.
This feels so amazing.
Great.
Hey, Professor.
Yeah, Blake.
When we're doing the weight, the atomic weight, what's the golden rule to follow for how many digits you should bring in?
Okay. This is my data. Well, let's go back to the original data. No, don't do that.
I don't want to nitpick.
No.
Magnesium 24.305. So I don't know if we can like round at the
Okay.
100th or.
Here's the problem, Blake. Look at my data. How many significant figures are in my data?
Just 3.
So in order to not take significant figures away from your data, your atomic weights need to have at least 3 sig figs in it. So if I
Okay.
would have wanted to, I could have used 24.31.
Gotcha.
If you use 24.305, you still are going to end up with 3 sig figs because this is limiting you to 3 sig figs. So that's
So it really doesn't matter.
as long as you use more significant figures in your atomic weight than your data has.
Gotcha. Okay, cool. Thank
If
you.
I was using 22.15, then I would have to use the atomic weight of 24.305. Does that
Understood.
make sense? Okay.
It does. Crystal clear.
Okay, remember guys, you can react products to products, reactants to products, products back to reactants, and reactants to reactants. Okay, percent yield. Very, very easy, guy. It's what you got over what you should have got, times 100. Bottom line, that's what it is. In a percent yield, what happens is you actually do the experiment and you determine how much of your product that you have. That's the experimental amount. That's the amount you retrieve. That's not necessarily going to be the whole amount that you could have gotten. You figure out how much you could have gotten by doing the stoichiometric problem. So you have the amount you retrieve in the experiment goes over the amount predicted by stoichiometry. You multiply that by 100. That is your percent yield. Guys, this is easy, right? Easy peasy.
Seems like it.
It's worth about 5 points on the test. You get blown away. You have a limiting reagent problem and you lose your mind. You go poof, you explode. Your mind explodes at that point. Keep the presence of mind to realize that percent yield is experimental value over amount predicted. And then put this formula in there. Once you put the formula in there, plug in some numbers. I'll give you most of the points for that. It would be real good if you remembered that. Sorry, hold on a second. I got a panicked wife here. She's getting a call from Petco. Sorry. I'll pay for that later. Sorry. Every now and again I have to throw in my little digs. Okay, so when you're doing a test problem, all right, it would be really good if you could look at the problem and see how much the experiment gave you. Plug that number into the amount retrieved and then make up something for the amount predicted. At least you'll get the points from the percent yield. What I'm trying to tell you is if you lose your mind on the first half of the problem, at least realize, hey, I could throw in some numbers for the percent yield and get some points from it. Does that make sense to you all?
Mm-hmm.
Okay, so the amount retrieved is going to be the amount that's going to be given to you in the problem. If you're doing the experiment, you would actually literally do the experiment, figure out how much you got back from that compound. That would be the experimentally made amount. That goes on top. The predicted amount is the amount that you predict by stoichiometry. You mix 5.034 grams of sodium phosphate with excess nickel 2 chloride and obtain 4.583 grams of sodium chloride. What is the percent yield? Okay, I'm going to go to the slideshow with this because the answer to my question is hidden in the next two responses. Jackson.
Yes.
What am I mixing together here?
Sodium phosphate and nickel 2 chloride.
Okay, good, good. At least you didn't answer sodium phosphate and sodium chloride. Does it make sense that you would mix sodium phosphate and sodium chloride and expect to get something different?
No.
Because if you do the double replacement, the sodium from the sodium chloride reacts with the phosphate to give you sodium phosphate, and the sodium from the sodium phosphate reacts with the chloride to give you sodium chloride. You just get the same stuff back again, right?
Yes.
So good, Jackson. You figured out what we were mixing together. Now, another important question I'm going to ask you. Is this a limiting reagent problem?
Yeah.
Okay, Jackson, have I given you two amounts of each reagent, or have I given you an amount of each reagent?
No. Okay. No. You've given reagent and then product.
What does excess mean to you, Jackson?
Excess means that it's not the limiting reagent. It's what's left over from the reaction.
Excess means that I have more nickel chloride than I need. So by this word excess, reading the problem, I am saying that automatically my sodium phosphate is my limiting reagent. I'm going to use that to figure out how much sodium chloride I could have gotten. Okay, David, done with you, Jackson. Good job, Jackson. David, you there?
Yeah.
All right, I got 5.034 grams of sodium phosphate. Can you tell me what the first step I need to do?
Change it to moles.
Change it to moles. Okay. First thing I got to do is I got to get a balanced chemical equation, though, David, don't I?
Mm-hmm.
Nickel 2 chloride. Can you give me the equation from, or the chemical?
It's going to be
formula?
NiCl2.
Guys, do you see how quick David did that? This is what you should be getting facile at doing. You should be able to see that nickel 2 chloride is NiCl2. How about the sodium phosphate, David?
I'm going to go on a whim and think that the phosphate's a -2 charge, so Na2PO4. Oh, well, I'm not sure what the charge of that is. Oh, it's 3. Okay, so Na3PO4.
Okay, so I got Na3PO4. Now what about my nickel phosphate? What did we say the charge on a nickel was?
It's charged 2, so it's going to be Ni3PO2.
Na3PO4 taken parentheses, taken twice. What about the NaCl?
It's going to stay the same.
We're good. We're good. We're balanced now. Rebecca. Thought I
Yes.
forgot about you, didn't you, Rebecca? Are my nickels balanced?
No.
What do I have to do?
Put 3 in front of the NiCl.
How about my sodiums?
No. Also put a 3 there.
3 here.
Yes.
Okay. Now we're going to do my chlorines, right? I've got a 3 in front of this NiCl2 that you just put there. How many chlorines do I have on the left?
6.
I've got a 3 in front of my NaCl. What do I have to do?
Change that to a 6.
Change that to a 6. Coincidentally, how many PO4s do I have on my left?
1,
How many PO4s do I have on my right?
2.
So what do I do?
Put a 2 in front of the NaPO4.
You're good. You're balanced, okay? We have our balanced chemical reaction. Thank you, Rebecca. Our next step, we're going to be converting to moles. And I'm taking my grams. I got 1 mole over the molecular weight. This gives me 0.03071 moles of sodium phosphate. I got to make my molar ratio. I use my balanced chemical reaction to figure out that I have a 6 moles of NaCl are produced for every 2 moles of Na3PO4. So I multiply 6 over 2 by 0.3071. I get 0.09212. I just multiply this by the molecular weight, which is 58.44. So I've done all that, guys, to say that under ideal conditions, I should get 5.383 grams of sodium chloride. But I didn't get that much. I didn't get that much. What I got was 4.583. In order to get the percent yield, I take the experimental value, what I did get back, divide that by the stoichiometric value, what I should have gotten back, multiply it by 100. This gives me 85.14%. Are we good here, guys? Questions? I'm hearing crickets, guys.
Okay, so I just want to like go over, because you went from the grams of the sodium phosphate, change that to moles, and then you compared.
Hold on a second. I'm sorry. I confused myself, okay? All right. First thing I did was I took the grams of the sodium phosphate, converted it to moles by dividing it by the molecular weight of sodium phosphate. This gave me the moles of sodium phosphate, 0.03071.
Right.
Then I looked back at my balanced chemical equation. I've got to relate my sodium phosphate to my sodium chloride. 6 moles of sodium chloride for 2 moles of sodium phosphate. So what I did now was I took my 0.3071 moles of sodium phosphate, multiplied that by 6 over 2. This gives me the moles of my sodium chloride. I need to have grams of sodium chloride. So I take this 0.09212 moles of sodium chloride, multiply that by the molecular weight of sodium chloride, which is 58.44, close enough. And I get 5.383 grams of my sodium chloride.
Okay.
We good? Okay. If I've got a limiting reagent problem, it's just the same thing. The only difference is I got to figure out what the limiting reagent is. And then the theoretical amount is the amount found from the limiting reagent. I got 0.2034 grams of nickel chloride, nickel 2 chloride, and 0.1727 grams of sodium phosphate. I obtain 1.583 grams of sodium chloride. What is my percent yield? Do you guys want to try this on your own?
Sure.
Am I hearing any objections to that? I'm going to give you 5 minutes on your own to finish this problem out, okay? I will be back. Just call me MacArthur.
Does anybody know what phosphate is? Is it PO3 or 4?
Phosphate's going to be PO4, right?
Yeah, it is.
Thank you. You said that one was 3 negative?
Yes.
Okay, are we being productive?
Yeah.
How far are we along? Can I go? Do I need to go through the solution, or are you guys still working?
I mean, I know what to do. I just haven't figured out the numbers yet.
Okay. We got the reaction. Does anybody want more time to do this? Okay, I think I need to shut the door. I'll be right back. Believe me, guys, I'm saving you from news about Trump. Okay. So, does anybody object to my going through the solution now? All right. We have a balanced chemical reaction. Next step, we're going to convert everything to moles.
Mhm.
I start off with 2 grams of nickel 2 chloride and 1.7 grams of sodium phosphate. And I end up with this many moles of nickel chloride and this many moles of sodium phosphate. Next step, I'm going to convert the moles of each of these into moles of my product. There's a relationship of 6:3, nickel chloride to sodium chloride. And there's a 6:2 relationship of sodium chloride to sodium phosphate. Brian, which one do I use? Which one am I picking?
The top one. Yeah, the top one.
So
So nickel
It-
chloride.
it produced the least. It produced the least. So that's the one we're going to use. And we're going to take that forward by multiplying by 58.44. Now this is the theoretical. This is the amount we determined by stoichiometry. That's going to go on the bottom of our percent yield equation. The amount I really got was 1.583 if I would go back to the beginning of the problem. I just divide that by my amount I got stoichiometrically, and I get a percent yield of 86.31. Are we good, guys?
Yeah.
Solid?
Mm-hmm.
Anybody have any questions about anything I've done? All right. Now we're going to go on to the hard problem. This is the problem that people freak out on all the time. And it's not hard at all, because all you're doing, you got to relate one reactant to another reactant. You got to figure out, if I have one reactant, how much of the other reactant will I use up? Then once you figure out how much of the other reactant you will have used up, you figure out how much you originally had of that reactant. And you subtract the two. That will give you the amount that you have left over. Ham sandwich wise, I made 8 sandwiches. This meant I used 16 slices of bread. I had 20. I subtracted the 16 from the 20. I have 4 slices of bread left. That's all we're doing here, guys. Don't get freaked out about it. By the way, in the midst of doing this, I'm also going to show you another way to figure out what the limiting reagent is. All right, we got our balanced equation. We're going to use the same problem we just had. 2.034 grams of nickel chloride and 1.727 grams of the sodium phosphate. How much of the reagent in excess is left? So I am going to pick one of the two. Either I'm going to pick nickel chloride and figure out how much sodium phosphate I need to react with all of the nickel chloride, or I'm going to pick the sodium phosphate and figure out how much of the nickel chloride I'll need to totally react with that. I think I picked the nickel chloride. Okay. First step, I'm going to need the moles of both of them. So if I have the 2.034 grams of nickel chloride, this means I have 0.01569 moles of nickel chloride. The 1.727 grams of sodium phosphate means I have 0.01053 moles of sodium phosphate. But in my reaction, I need 3 moles of nickel chloride to react with 2 moles of sodium phosphate. So if I pick my nickel chloride, I'm going to multiply my nickel chloride moles by 2 moles of sodium phosphate over 3 moles of nickel chloride, and this will tell me how much sodium phosphate I will use up if I have 2.034 grams of my nickel chloride. So I take my 0.01569 times 2 over 3. This means I would have used up 0.01046 moles of sodium phosphate. Did I have that much? Remember, I had 1.727 grams, which converted to 0.01053 moles of sodium phosphate. Okay, this is how much sodium phosphate I will have used up if I start with 2.034 grams of nickel chloride. Does that make sense to you all?
Yes.
Now, this is the amount I would have used up of sodium phosphate if I had to use up all my nickel chloride. Now, I have 0.0153. Did I have enough?
Yes.
If I had enough of the second reagent, that means that the first reagent will run out before the second reagent will. The first reagent will run out, leaving a little bit of the other reagent left. This is the amount I used up from my nickel chloride. This is the amount of sodium phosphate I used up. This is the amount I started with. So in order to figure out how much is left, I subtract the amount I used up from the amount I started with. That ended up with 0.0007 moles left. I multiply that by the molecular weight. And I end up with 0.1 grams of sodium phosphate left over. Questions? Anything? Any questions, guys? Is this making sense to you?
Yeah.
Okay. Again, I just want to reiterate. If this is another way to determine limiting reagent. You have the two reagents. You figure out if you have this much of the first reagent, how much of the second reagent will I have used up? You then figure out how much of the second reagent you originally had. If the amount you would have used up is less than the amount you had, then the first one is the limiting reagent. If you have too much produced by the first reagent, then the second reagent is limiting. Just keep that in mind. It's another way to prove limiting reagent. Okay. Okay. I will go through this. I have time. It's not the only way to do the problem. Remember, I had this much sodium chloride that I produced from my nickel chloride. Remember, I had this much sodium chloride that would have been produced by the sodium phosphate. This one's smaller, so it came from the limiting reagent. Now, if I subtract these two numbers, what that tells me is that is the amount of sodium chloride that was not produced. So I I figure out the amount of sodium chloride that was not produced. By subtracting, this is the amount that was not produced. I use the mole ratio of sodium chloride to sodium phosphate, which is 2 to 6. That gives me my same number of 0.0007. I then multiply that by the molecular weight. I come up with the same answer. The only reason I went to illustrate that, there's more than one way to kill this beast. Okay? Another problem. I have 343 grams of lead 4 nitrate and 182 grams of aluminum chloride. How much of the remaining reagent is left? Blake, what am I going to do here? What's the first step?
Well, I see it's already balanced. So you'd convert the grams to moles.
Get both of them, convert the grams to moles. Okay? Then what I am going to do is I am going to pick one of my reagents. In this case, I picked my lead nitrate. I figured out how much aluminum chloride I would use up if I used up all that lead nitrate. So I got multiplied by 1 over the molecular weight, got the moles of lead nitrate. I took my moles of lead nitrate, multiplied it by 4 over 3. I would need at least 1.00 moles of aluminum chloride. Subsequently, I figured out from the aluminum chloride and the molecular weight of aluminum chloride that I had 1.37 moles. Did I have enough?
Yes.
If I had enough, then the first reagent is the limiting reagent. All I have to do is subtract the amount I used, which is the 1 moles from the 1.37 moles. This means 0.37 moles of my aluminum chloride was not used. So that's 0.37 moles of aluminum chloride not used. Multiply that by the molecular weight. I have 49 grams of aluminum chloride left. I got 10 minutes and one more problem, guys. This is it's a different twist on it. Up to this point, when I've picked a reagent, and compared it to the second reagent, I always had enough, right? The 2 previous problems, I had enough. I got to show you what happens when you don't have enough. When in actuality, the second reagent is the limiting reagent. Are we good with that? That's the last problem, and then we can flitter off to the night. I'm reacting sulfuric acid with aluminum hydroxide. I have 47 grams of sodium of sulfuric acid and 33 grams of aluminum hydroxide. How much excess reagent do I have? Okay, I'm going to pick the aluminum hydroxide. My molecular weight of aluminum hydroxide is 78 grams per mole. So I divide the 33 by 78, I get 0.42. There are 3 moles of sulfuric acid for 2 moles of aluminum hydroxide. I take my moles of aluminum hydroxide, multiply that by 3 over 2. This gives me the moles of sulfuric acid that I need. Do I have it?
No.
I don't have it. This means I have less sulfuric acid than I need. If I have less sulfuric acid than I need, it is the limiting reagent. Did we get that one down? Are we okay with that? So it's just the same concept as we did before, only it's not a direct subtraction. Right now, because the sulfuric acid is the limiting reagent, I got to figure out how much aluminum hydroxide I used up. So I got to take my moles of sulfuric acid and multiply it by 2 moles of aluminum hydroxide over 3 moles of sulfuric acid. This gives me 0.32 moles of aluminum hydroxide used up. I had 0.42 moles of aluminum hydroxide because this is the original number of moles I got from my 33 grams of aluminum hydroxide. I had 0.42. I used up 0.32. So I have 0.10 moles of sulfuric acid left. I multiply that by my molecular weight of aluminum hydroxide, and I get 7.8 grams left. Okay, we've worked a lot of stoichiometry problems between this period and the last period. I've got another 5 minutes or so, guys. Is there anything I need to clear up for you? Remember, stoichiometry, find moles of known by dividing by molecular weight, change to moles find moles of known by dividing by the molecular weight of the known. Then we are going to change to moles of unknown by using the molar ratio found by the balanced chemical equation. Then we are going to determine the grams by multiplying the moles of unknown by the molecular weight of the unknown. I recognize a limiting reagent problem because I am given 2 different amounts, or I'm given amounts of 2 different reactants. I find a product. I find out how much each one of those reagents will make of that product. I choose the smaller one. That's the one I report out. Percent yield is simply the amount that I retrieve from the experiment divided by the stoichiometric amount. Excess, I use one of my reagents to figure out how much of the other one I need to react with it completely. I figure out how much of the other reactant I have. If I have more than I need, then the first reactant is the limiting reagent, and that is the one that I subtract from the amount of the other one I had originally. That gives me the moles of excess. If I'm doing an excess reagent problem and I pick my first reagent and I have more of my first reagent than I need of the second reagent, that means my second reagent is limiting. I got to use the second reagent to figure out how much of the first reagent I used up. Then I subtract that from the moles originally I had of the first reagent. If I'm confusing you further, I apologize. I just wanted to summarize everything up. Any questions after that diatribe? Okay, be prepared. We're going to start solutions on Thursday. I'm hoping to get through solutions and acid bases on Thursday so that on Tuesday, next Tuesday coming up, we can start the gas laws. Next test will be stoichiometry, gas laws, and solutions, acid bases.
Sounds good.
Those of you that I'm going to see, I will see you again at 7:30 because I need to have some time to record, to process this, this video. Just a word of caution, at least the first 10 minutes of the class are going to be talking about the laboratory notebook. If you don't want to listen to that, then I would encourage you to wait until 7:40 before logging in. The experiment we're doing for this week is not that complicated, but there are some nuances I want to make sure you know. Okay, guys, see you on Thursday then.
Thank you.
Thank you. Have a good one.
Blake,
Thank you,
David.
Professor.
Yeah, I'll see you all in about 50 minutes.
Sounds good.
Take care.
Bye.
Bye. Min, you doing okay? Min. Okay, man. Take care. I'm stopping sharing. And now we are going to reach the end.